Hello everyone, I'm Jaren Mane, a PhD student at KU Leuven, and I'll talk about our NeurIPS paper, Embeddings as Probabilistic Equivalence in Logic Programming, which is joint work with Eftimi Atsamura. On a high level, the setting we're tackling is combining logic and neural networks and so-called neurosymbolic models. And we want to do this in a way such that both the logic and the neural networks can be trained jointly in an end-to-end differentiable fashion and without suffering from local minima or degenerate optima. Let's look at an example. Let's say we want to classify image sequences. In this case, we have some sequence of image digits that may be accepted or not accepted. The goal is then to learn both the digit classifier, so the neural network, which predicts whether each image is a 0 or a 1, and to train a automata which will have different state transitions such that the language is either accepted or not accepted. So in our paper, we propose an end-to-end differentiable prover that does not suffer from convergence issues like has been the case for past systems. Like in this case, on some toy grammars, you can see that our system considerably outperforms the state-of-the-art in terms of accuracy. How do we do this? Well, the main contribution is that we propose a new probabilistic logic programming semantics, which is based on equivalence and not on facts. What does this mean? Well, in a conventional probabilistic logic program, you have some rules and some facts. And these facts have a probability associated with them. Like in this case, B has 10% chance of being true. This in turn then essentially gives you a distribution over your logic programs by choosing which facts are true and which are not. On the other hand, we have a distribution over equivalence relations of the symbols of the program. In this case, A, B, C, and D, which either may be distinct from each other or, for example, here, B and D are the same. That means, even though here we need B, and we have the fact D, as they are equal to each other, now we can prove A. So in summary, the probability of an atom is the expectation over equivalence relations, where for each equivalence relation, we will check if the program saturated to this equivalence relation entails an atom. So the saturation basically formalizes this notion that the program must satisfy this equivalence relation. You can see these probabilistic facts and probabilistic equivalence as somewhat orthogonal. You always have a certain base program which can prove atoms. In this case, this area is denoted as a gray box. By having a probabilistic fact distribution, you then assign a probability that certain atoms are true or not. With probabilistic equivalence, on the other hand, we're placing uncertainty of atoms that could not be proven in the base program. So this gives us a system which has probabilistic semantics, which can do structural learning, which means that we can learn different rules that are not present in the existing program, that is still multilinear, meaning that it's relatively straightforward to optimize, and which is open world, so we can prove things about symbols that do not appear in the basic program. I'll just finish with a summary of our technical contributions. So firstly, we propose a new probabilistic logic programming semantics based on probabilistic equivalence. Secondly, what I didn't have time to talk about here is we showed that you can use embeddings as a way to kind of factorize these distributions you have over equivalence relations. And lastly, we proposed inference techniques, both exact and approximate, which use optimizations proposed before in the database community. For more details on how this works, I recommend you to take a look at the paper.